Okay, hello classmates. This is problem number 3 on the group work assignment, which says a 10 loop 5 centimeter diameter coil carrying 2.5 amps of current lies centered at the origin on the XY plane. What is the strength of the magnetic field at a point 7.5 centimeters above the coil on the Z axis? So we drew that little picture that's sitting there with our coil centered at the origin, and we have some point that's on the Z, along the Z-axis at 7.5 centimeters above that. So off to the left, we have the current of 2.5 amps. We have 10 loops in our coil, and then those numbers that I talked about. 7.5 is the distance, and our radius is from that 5 centimeter diameter coil. So that's what we are working with, and we decided to start out with the Biot-Savart law.
Yes. So the Biot-Savart law, this is kind of a condensed form of it. Normally you'd notice that we'd have I times delta S crossed with R, but in this case, we'll form a relationship with cosine of the angle between them. And for this particular instance, there's actually a derived example in the text that we used, which after a lot of summations and drawing relationships between this angle and this R and the height and radius of our circle, we end up with this expression. So it's pretty lengthy, so we would refer you to example 32.5 in the textbook for the full derivation if you'd like to see it. But this is our relationship that we end up with, and it's pretty common in the textbook to see the Biot-Savart law derived as such. And so with this right here, this is for a single loop. And so in order to find out what our magnetic field is with 10 loops, or with a given number of loops, we just multiply it. And that works as long as our loops are tightly wound, which we can assume that they are in this case.
Okay, so there are each of our numbers. Again, that n will equal 10 because of the number of loops. And we have that, the constant, 4 pi times 10 to the negative 7th, with our current and our radius that we've converted into meters. And then, of course, the z and the r, the radius at the bottom. So calculating that out, figured it to be magnetic field is about 19.87 millitesla. And so that is the magnetic field answer for problem number 3.
Yep. And here's our unit analysis here, and it does come out to Teslas, which is a good thing. And just a quick note, this right here, you'll notice it looks kind of like the Pythagorean theorem. That's because it is. That's where this comes from. This is originally that R up here turns into this. So, all right. Thanks for watching. Hopefully that makes sense. Comment if you have questions. If you have questions.